Soil parameters can be divided into three categories: physical, chemical, and biological. This short video will cover a brief introduction to the physical properties of soil. Physical characteristics of soil are related entirely to particle size and how they are distributed throughout a soil column. So, I'm sure you've had experience with sand, whether it's from a play box or at the beach or anything like that. Very coarse, very large. You can see individual pieces. You could count them if you wanted to spend the time. Silt, you can basically think of this like flour. And so you're not really counting individual pieces. You might technically be able to see them, but there is no way you're ever counting them. And then clay, as we've covered, this is something like for ceramics or anything that's really sticky. There's absolutely no counting it. You can't even separate individual pieces if you tried. So and these characteristics come into play with how a soil acts. You know, the physical characteristics of a soil are based upon how these particles, the size of them, and how they are arranged in a space. After particle size, the characteristics we need to talk about is bulk density. Bulk density is a measure of mass within a given volume. Bulk density introduces this concept of mass within a given volume. And so even though soil particles are presumed uniformly dense, that does not mean that they occupy a uniform given of volume. Soil, even if we might look at it as a single surface with which we interact, something that is just mass, there's actually a lot of volume in there that is not soil. And we call this pore space. And so soil has a pore space distribution on average of 50%. What that looks like for a soil can be viewed as if this is all the soil that you've dug up, half of what you're holding is actually not soil. So soil, not soil, even if all of this is in your hand. What that means, really, give or take half of that not soil space is water. And the other half is air. And in this space, this is the mineral portion. This is the solid mass. These are the soil particles. And so what you might be able to see is that soil has an average density, not soil particles, but soil itself, of about 1.3. Right? If solid particles are 2.6, but half of soil actually is not soil particles, then soil is only about 1.3 grams every cubic centimeter. We can further break down this mineral portion, of course, into sand, silt, and clay. There's also a small fraction. There's actually a small fraction of organic matter, typically less than 5%. While they're technically particles and they are physical objects, this is much better discussed within biological parameters, and so we won't be doing that in this video. Another way to look at this soil pore distribution is using this graph here. So this is another way to look at pore size distribution within soil. So again, we've got an average of 50%, right? So the volume of soil, the entire soil that you've scooped out of the earth, is actually 50% not soil itself. 25% air, 25% water, the rest of it is actually the soil. So this is where we get volume of our pore space distribution being about half, and thus soil particle density yielding an average soil density of 1.3 grams per cubic centimeters. Pore space distribution is important because since soil particles are presumed to be wholly dense, there is no space within a particle this is the only area for soil life to live. So we're not talking about biological parameters. However, the physical parameters of soil, the soil particle size, and the distribution of its pores shows us that this is the space that soil life has to live. We've got some that live in air, some that live in water, most of them living kind of in the flux between, but pore space is required. If you have no pore space, if your soil is wholly compact, there is nothing really alive in there, because you're not actually going to get purely compacted soil, but you've basically stamped the life out of it if you've lost air and water. What can live without air and water? Soil life lives within the pores, and these pores develop into a kind of network of pipes. And these pipes yield something called hydraulic conductivity. Hydraulic conductivity is just what it's how well water can move through a soil. And so again, if the soil is wholly compacted, water can't get through here. This is utterly solid. It's 2.65 grams per cubic centimeters. There's no room. Water moves through pores within a soil. And so depending on how these pores are distributed in a soil tells you whether or not your plot will, be flooded when it rains, and how long it will take that plot to finally drain after the rain has ceased. Or you might have something like this where you can see, even right through here, there's already soil. This puddle is receding. It has rained, yes, but the soil is absorbing it into its pores. The other side of soil porosity, and tied with hydraulic conductivity, is actually soil aggregation. Soil aggregation refers to how the soil clumps together and the pieces, the actual big pieces of soil that you can see. So not these individual pieces here, but as you're digging in the dirt, it's like the clods of dirt that you can pick up and break apart into further smaller clods. Aggregation is not just the pieces that you can see and how well you can break them apart. It's how they're situated within the greater soil profile. So if we have two fields, and one of them is perhaps an undisturbed meadow, what we're going to see is undisturbed soil aggregates here. And so regardless of how fast or how slow the soil microbial life is in this area, and how well these pores are being connected and increasing hydraulic conductivity, ultimately what we're going to see is a network of pores that create interconnected tunnels within 3D space, of course. But these pores are between all these greater soil aggregates. So we have, bigger soil chunks here and all this. And of course, in between here, this is pore space as well. However, it's not connected like this. But ultimately, what we're going to see with this soil aggregation is, again, it goes back to the hydraulic conductivity. How well can the water come down and drain through, say, a wormhole than if you have a plowed field? If you have a plowed field, what you do is bust up all these large soil aggregates into all the tiny fine pieces, and water is mostly going to be pooling up and slowly seeping through. What I hope you're picking up on here is that even though we're talking about physical parameters and that they are inert and not alive, they're very much tied to biological parameters, because life exists within the space that these physical parameters give them. Okay, let's take a quick look at a video, a time lapse of worms feeding, and we can see some stratified layers within the video. What you're seeing, hopefully, is this mixing of the media. Even though these particles are very fine and there's not much aggregation itself, we still see some pores developing. You see tracks where the worms are running through. You can see that there are definitely spaces within the soil being developed. And so these are physical parameters being greatly affected by biological parameters. Really, ultimately, this is a self-fulfilling feedback loop, right? Biology requires pore space to thrive. Pore space tends to lend itself towards greater biological life, and so we kind of get both of these factors accelerating throughout the life of the soil, so long as nothing interrupts it. Speaking of disruption, here we can see the differences in aggregation between this relatively undisturbed soil and what we can call a plow pan right here. And so when the plow comes through and scoops up this soil, it does create a very fine tilth at the top. However, at the bottom of the plow, it is smashing all the particles together and making this root unable to pass. That's it for the physical parameters of soil, one of 3 broad categories of soil parameters.